welcome. We are in a photoelasticity module. So, we are discussing the basics of optics, which we know from our simple harmonic motion knowledge. So, in the last class we have discussed the linear polarization, or rather the superposition of two light wave in a same plane with same frequency, but different amplitude. So, if we consider the we have also seen the equal amplitude case, what will be the intensity of light, because all polariscope and all those things, the instrument by which we will use for the photoelastic experiment, the intensity of light is the quantity that is required to be evaluated. So, here in today we will consider the superposition of out of plane waves. So, here this let us consider two simple harmonic wave fronts with similar frequency, but different amplitude. So, this will be E x and E x. So, let us consider that the one of the wave is E x is A x cos of 2 pi by lambda x 0 plus delta x minus c t, and similarly we can write it E x is A x cos phi x minus omega t, and but the frequency is same for two light waves. So, that is E y is A y cos of phi y and omega t. So, now dt, but the characteristics of these are the out of plane waves. So, not in a plane. So, when we have out of plane waves, so we can now write the resultant wave is root over E x square and E y square. So, this is phi x and phi y are the phase angle associated with wave E x and E y. So, now what will be the, in this case what will be the resultant wave? In the previous lecture we have seen, if it is in plane, then we can just add it, just E 1 and E 2 we have seen, but in case of a out of plane means if the two waves are out of plane, then it is E x square and E y square, that we know, right. Now, if we now do some manipulation and try to eliminate the dependent part, time dependent from both the waves, then we arrive an equation of this form. This equation, if you look carefully, this equation is nothing but a elliptic equation. So, here E x square by A x square minus 2 E x E y by A x A y cos of 2 pi delta by lambda, and then E y by this thing. Now, phi y minus phi x is 2 pi delta by lambda, where delta is delta y minus delta x. Now, this equation is an equation of an ellipse. So, if I write it in a graphically, if I show it graphically, so this is actually the E for the root over of E x square minus plus E y square, and this is A y and this is A x. So, this is E x and this is E y. So, that is why this is A x and A y. So, the amplitude. Now, this since this represents an equation of an ellipse, so this we can say it is elliptically polarized light. Now, if I if I consider a special case of polarization, for instance, when A x and A y equals to A and delta is 2n plus 1 pi 2n plus 1 by 4 pi, then I can see that if we substitute in the previous equation these conditions, that delta is 2n plus 1 4 by pi 2n plus 1 by 4 into pi and Ax and Ay is A, then we obtain an equation of an circle. The elliptical equation becomes a circular equation. So, we say circularly polarized light. So, when essentially two out of plane waves, if we superpose, then we get a polarization. The resultant wave is a polarized light, and this polarized light is essentially depending on certain magnitude and phase difference, it either elliptically polarized or circularly polarized. Now, if delta equals to n pi n lambda by 2, then it will represent an equation of a line. So, this is called linearly polarized light. So, that means that if I just substitute n equals to 0, 1, 2 and so on. So, if I substitute, then I see that this will represent a equation of a straight line, and then this we call as a linearly polarized light. So, in an essence, what it is actually that it gives you polarization when you have two sets of wave, you superpose and then you get the resultant wave. The result, it is trying to we are trying to understand what will be the characteristics of the resulting wave. So, essentially this is the principle of a polariscope. So, when you design a polariscope, essentially you need to look how a unpolarized light enter into this polariscope and how it goes out from the polariscope. So, basically the polarization part of the light. So, this polarization can be achieved in a different way also, for instance reflection, reflector or refractor, through that also it can be obtained. So, now reflection and refraction, we know the Snell's laws and all those things from our basic plus 2 level knowledge. So, when a ray of light strike at a surface or two transparent medium with a different refractive index, the ray is divided into two portions. One is called reflection, another is called refraction. So, the reflected ray comes back in the same surface of the first medium, refracted ray transmits into second medium from the surface. So, these things we know, but just to review our or to study the essentially the photoelasticity, we need to review this. So, for instance, the reflection is when alpha and beta are same in this picture. So, this is a interface. So, this is material 1 and this is material 2. So, when an incident ray comes, so it is reflected. When alpha and beta are same, then it is called pure reflection, and then when some of the rays goes in the second medium. So, if this is a gamma, this with the normal, if this makes a gamma, then sin alpha by sin gamma is n2 by n1, or that is the refractive index of material 1 with respect to vacuum, and n2 is refractive index of material 2 with respect to vacuum. So, n21 is the ratio n2 by n1 or refractive index of the material with material 2 with respect to material 1. So, the laws of reflection and refraction provides only information regarding the direction of the reflected and refracted rays. So, basically this N1 and N2 is the medium property which affect how the light reflects and refract in a medium. So, this thing we know it from our previous knowledge. Now, the information related to the intensity of light is obtained from the Maxwell equation. So, Maxwell equation, even though we will not discuss it here, so it is better to know that is coming from the Maxwell equation. When an unpolarized light incidents on a surface, the waveform can be resolved into a two direction. One is this is unpolarized incident ray, and then one of them can goes out. So, parallel component and the there are a perpendicular component also perpendicular to this plane, and then this refracted ray in the polarized part, the parallel component actually vanish. So, both of these waveform have same intensity. So, and this is how the intensity of the intensity of the incident ray and intensity of the reflected ray, how it is related with the reflection coefficient R. So, this also we have seen in our previous knowledge. So, now the basic idea of this to construct a polariscope. So, it is an optical instrument that use properties of the polarized light in its operation. For experimental stress analysis, we generally use a circular polariscope, but plane polariscope is also used. So, it uses plane polarized light which is produced by plane or linear polarizer. So, we have we know now what is linear polarization of the light means. So, when you have two superimposed or the unpolarized light, when it gives certain properties which we have studied in the previous lecture. So, now circular polariscope, it uses polarized light which requires linear polarizer along with a wave plate essentially. So, essentially circularly polarized light. So, the equation of the light vector becomes circular, or equation of a circle that we have seen in this previous slide. So, this is known as the circular polarizer. So, now this finally, if we look the linear polarizer. So, when a light wave strikes in a plane polarizer, the optical element resolves into two orthogonal direction. One is parallel to the axis of the polarization. So, if I consider this is the axis of polarization. So, if this is my red one is my light vector, and if it makes an axis of the polarization with alpha t. So, it's alpha, and then I can do it in a component wise. So, in this component wise, one component will be parallel to the axis of the polarization, this one, and perpendicular to the axis of the polarization is this one. So, if I consider this is a axis of polarization. So, if the incident light vector can be written as this. So, E is a cos, just a simple harmonic wave, and then initial phase angle is not important. So, I can write it as a cos omega t. So, the absorbed and transmitted component of the light I can write E t is a cos omega t into sin alpha, and E a the absorbed part of the light is E a cos omega t sin alpha. So, a cos omega t sin alpha. Now, so I think this will be cos alpha. So, this will be cos alpha. So, E a will be a cos omega t cos alpha. So, actually this is the axis of polarization. So, this will be cos alpha I think, and this will be sin alpha I think. So, this will be cos alpha, I think this will be sin alpha. So, so axis of polarization along that is E t, and perpendicular to that is E a. Now, this once you in case of a circular polariscope, again this is doubly reflected plate, and this wave plate is an optical instrument which can resolve incident light into two orthogonal direction. This type of polariscope actually we use. So, if index of refraction is n2 and velocity of propagation is c2, then c1 and c2 if it is greater than, then the two medium that we are considered, which is having refractive index n1 and n2 and velocity of propagation is c1 and c2, then how we can resolve any incident light wave. So, one axis will be faster, one axis will be slower. So, now this can be resolved into two, E t cos beta and E t 2 is sin beta, which with the previous expression we can write this into a this form. Now, this kind of material is called doubly refracting or temporary the temporary doubly refractive material we are talking about in the previous class. So, this property is essentially known as the birefringence. So, now these are the basic principles of designing the polariscope. So, which naturally is very important to us, because we will be using this polariscope in our photoelastic measurement. So, now arrangement of optical elements in a polariscope. So, this is essentially a linear polarizer, where if this is a model location and if this is a light vector going through it. So, there and the axis of polarization for the polarizer will be perpendicular, and this is one of them will be perpendicular and another will be the orthogonal to the other direction. So, this is a setup for plane polariscope, and this is a setup for circular polariscope, where essentially use a two circular two different refractive index material, and then you have one axis of polarization, and there is in the other direction axis of polarization. So, this is the basic principle how circular polariscope works in the photoelastic measurement. So, now another thing that is important, we will not study it in detail here, rather we will just understand or we will discuss it. Those who really want to understand it, they can go through the experimental stress analysis by Daly and Rayleigh. So, this is moire fringes. The moire fringes is it is a French word. Actually, this is a special type of material is known as the watered silk. So, if you look at the most right hand side picture, then you will understand that if you place these two grated body, and then you see the inner layers are very much visible in this common zone. So, this is moire effect is observed when two similar but not quite identical arrays of equally spaced lines or dots are arranged, so that the one array can be viewed through the other. So, that is identical or may not be identical. So, this generates some patterns in a body. So, this is also helpful for our case. Now, in the essential mechanism of the moire fringes is an array of lines are referred, which you have seen earlier. This is grids. When two perpendicular grids are employed on a specimen, it is called cross gratting. So, gratings are overlaid in the specimen by photographic emulsion or contact printing or any other means. Then the spacing between these grids or of parallel lines are measured through the comparators or microscopes before and after the loading of the specimen, and the displacement and strains are measured. So, one is reference grating. Essentially, it is a correlation. The direction perpendicular to the line of the master grating are primary direction, and the direction parallel to the lines of the master grating are secondary direction. So, there are two gratings, one is reference grating and another is specimen grating. So, when you compare these two gratings, essentially you get the strains in the body. So, how if you see, so this is a model information. So, this is a reference plate, and then this light transmission through a match and aligned model. So, this is essentially from Daly and Rayleigh. I just represented pictured it for you for just to understand what is it. And so, this is a reference grating. If you see, this is the pitch here, and so we can calculate from this p and p dash the center to the center distance. These are center to center distance. So, we can calculate the strains in the body. So, for instance, if p is the center to center distance between master grating or the pitch of the grating, and then p dash is the center to center between model grating or pitch of the model grating, then Moiré fringes can be written as this. So, delta L by L 0, which is essentially the tensile strain, and so in P is the number of Moiré fringes per gauge length. So, gauge length also we know that number of Moiré fringes in that gauge length. So, that is N, and then if I g is the gauge length, then 1 minus N p is my L 0, and 1 plus L g 1 plus L 0 is my for compressive strength. So, this is the formula for the Moiré fringes. So, now this is just to introduce the topic to you. We are really not will be doing these things. So, this required some experimental setup also to understand these things. So, in a overall sense, what was our objective here, just to introduce the what is Moiré fringes and how the objective of it we can calculate its strain patterns. Essentially, it is comparing two gratings. One is master grating, one is secondary grating. So, one is associated with the reference point and one is reference body, and one is associated with the model for which we are which will be evaluating, for which we will be evaluating the grating. So, by comparing these two grating, we can essentially find out the strains in the body. So, so what we have discussed here, we discussed the two types of polariscope. One is linear polariscope, another is circular polariscope. The circular polariscope, which we will be mostly using in our experimental setup, and this circular polariscope is worked on the how it worked, because it two out of plane lights, if we superimpose, essentially we get an equation of ellipse, and under certain condition, that is if the amplitudes of, for instance, the amplitude of the lights are same, and then the phase difference, if we arrange the phase difference of these incident waves in such that that delta is 2n plus 1 by 4 into pi, then we get a equation of that ellipse is transformed to a equation of a circle. So, then we get the resultant wave is circularly polarized light, and using this principle actually we conduct the photoelastic experiment. So, this is overall theory of the polariscope, and how we have also seen how the circular and linear polariscope can be, what are the components of the circular and linear polariscope. So, this the objective is to give you an idea how this photoelastic experiments happens. So, in the next class actually we will discuss what is the stress ellipsoid and how it is essentially related to the refractive indices, and how we can really conduct if we have a photoelastic body or photoelastic model, and if we load it and then try to find out the fringes pattern, if we observe the fringes pattern, how really we can find out the stresses in the body, and how we can really calculate the stresses in the body. So, based on the number of fringe patterns and other quantities. So, in the next class we will start the theory of photoelasticity, by which most of us will do the experiments. So, I stop here. Thank you.